something enormous is hiding at the edge of the observable universe. A structure so vast, it bends the limits of cosmology itself. Gamma-ray bursts scattered across billions of light-years trace a pattern no model can comfortably explain. A feature so old, so wide, and so improbable, it almost shouldn't exist. If you enjoy these deep dives, you can subscribe. It helps more than you think. So, let's begin. The Earth you're standing on is about 4 times wider than the Moon. Not an enormous difference, really. You could line up 4 Earths and roughly match the Moon's orbit around us. But step back a little further, and the scale starts to shift. Jupiter, that banded giant in our outer solar system, could swallow more than 11 Earths across its equator. You could fit over 1,300 Earths inside Jupiter's volume, though most of that space is hydrogen and helium, not solid ground. Jupiter is vast, and yet it's still just a planet. The Sun is something else entirely. If Earth were the size of a marble, the Sun would be a sphere about as tall as a person. You could line up 109 Earths across the Sun's diameter. 1 million Earths would fit inside it. This is the star that governs our existence, the reason we have warmth and weather and life, and it's fundamentally different from the worlds that orbit it. The Sun isn't a ball of rock or gas held together by its own gravity alone. It's a nuclear furnace, fusing hydrogen into helium, releasing energy that takes thousands of years to work its way from the core to the surface before streaming across space to touch your skin. And the Sun is small. There are stars in our galaxy that would make the Sun look like a grain of sand on a beach. Scuti, one of the largest known stars, has a radius more than 1,000 times larger than our Sun. If you replace the Sun with Scuti, its surface would extend past the orbit of Jupiter. The Earth, Venus, Mercury, Mars, all of them would be inside the star. These red supergiants are dying stars, bloated and unstable, burning through their final reserves of fuel before they collapse. They're massive, but they're also diffuse. The density is so low that by our standards, much of a supergiant's outer layers would qualify as a vacuum. Even these enormous stars, though, eventually run out of fuel and collapse. When a massive star dies, if it's heavy enough, it doesn't just fade away. It implodes. The core compresses into something so dense that gravity becomes overwhelming. A stellar mass black hole forms, an object where all that mass, sometimes dozens of times the mass of the Sun, gets compressed into a space smaller than a city. The gravity is so intense that not even light can escape once it crosses the event horizon. The size of that horizon, the boundary beyond which nothing returns, might only be a few dozen miles across. Everything that made the star what it was, all its light and energy and heat gone. Just gravity remains. These stellar black holes are small compared to what we find at the centers of galaxies. Supermassive black holes don't form from the collapse of a single star. They grow over billions of years, feeding on gas and dust and sometimes entire stars, accumulating mass that can reach millions or even billions of times the mass of the Sun. Sagittarius A star, the supermassive black hole at the center of our Milky Way, is about 4 million times the mass of the Sun. Its event horizon would fit comfortably inside the orbit of Mercury, but there are much larger ones. TON 618, one of the most massive black holes ever observed, is roughly 66 billion times the mass of the Sun. Its event horizon spans about 242 billion miles. That's 40 times the distance from the Sun to Pluto. These objects sit at the centers of galaxies, and galaxies themselves exist on a scale that makes even supermassive black holes seem like tiny anchors in an ocean of stars. The Milky Way is about 100,000 light-years across. A light-year is the distance light travels in a year, moving at 186,000 miles per second. That works out to about 6 trillion miles. So the Milky Way spans 600 quadrillion miles from edge to edge, a disk of stars and gas and dust, spiral arms turning slowly over millions of years. And we're just one galaxy. Andromeda, our nearest large galactic neighbor, is a bit bigger than the Milky Way and sits about 2.5 million light-years away. It's close enough that we can see it with the naked eye on a dark night, a faint smudge of light that represents 1 trillion stars. In a few billion years, Andromeda and the Milky Way will collide, or rather merge, their stars passing by each other in a slow-motion dance that will take millions of years to complete. The distances between stars are so vast that actual collisions will be rare. Mostly, the two galaxies will just distort each other, their shapes warping under mutual gravity until they eventually settle into a single, larger, elliptical galaxy. But even large galaxies aren't the largest structures. Galaxies cluster together, drawn by gravity into groups and clusters. The Milky Way and Andromeda are part of the local group, a collection of about 80 galaxies spread across roughly 10 million light-years. That's already a distance hard to fathom, but the local group is small compared to galaxy clusters like the Virgo cluster, which contains over 1,000 galaxies and spans about 33 million light-years. The Virgo cluster, in turn, is part of something even larger. Superclusters are collections of galaxy clusters, massive chains and sheets of galaxies that stretch across hundreds of millions of light-years. The Virgo cluster, along with the local group and dozens of other galaxy clusters, forms part of the Laniakea supercluster, a structure about 500 million light-years across. The name means immense heaven in Hawaiian, and it's an appropriate label. Laniakea contains roughly 100,000 galaxies, each with billions or trillions of stars. The whole thing is slowly being pulled toward a region of space called the Great Attractor, a gravitational anomaly hidden behind the plane of the Milky Way, difficult to observe directly, but undeniably there. And Laniakea, vast as it is just one supercluster among many. The universe is filled with them, separated by enormous voids where almost nothing exists. These voids are regions hundreds of millions of light-years across, nearly empty of galaxies, just vast expanses of space with a few scattered atoms drifting through the darkness. The voids and the superclusters together form a kind of cosmic web, a network of filaments and sheets where galaxies collect along the threads, leaving the voids hollow. This pattern, this large-scale structure, tells us something about how the universe evolved. After the Big Bang, matter wasn't distributed perfectly evenly. There were tiny fluctuations, regions where the density was just slightly higher or lower than average. Over billions of years, gravity amplified those fluctuations. Denser regions pulled in more matter, forming stars and galaxies. Less dense regions became voids. The result is the web we see today, a universe organized not as a random scatter of galaxies, but as a structure, almost biological in appearance, like the neural networks in a brain or the mycorrhizal networks in a forest. But there are limits to how large these structures should be. According to our best cosmological models, structures shouldn't exceed about 1.2 billion light-years across. That limit comes from the age of the universe and the speed of light. The universe is about 13.8 billion years old, but it's been expanding since the Big Bang. In the early universe, regions of space were closer together. Gravity had time to act, pulling matter into clusters. But as the universe expanded, especially as the expansion accelerated due to dark energy, regions that were far apart had less time to influence each other. There's a point, cosmologically speaking, where structures should stop forming, because the expansion carries matter away faster than gravity can pull it together. That limit of 1.2 billion light-years isn't arbitrary. It's based on our understanding of gravity, the distribution of matter, and the expansion rate of the universe. Most observed structures fit within this boundary. The Sloan Great Wall, discovered in the early 2000s, is a cosmic filament about 1.4 billion light-years long. That's already pushing the limit, large enough to make cosmologists take note, but not impossible to explain. It could be seen as a statistical fluctuation, a region where matter happened to cluster more densely than average, right at the edge of what's plausible. And then there's the Hercules Corona Borealis Great Wall. It was identified in 2013 by analyzing the distribution of gamma-ray bursts, which are among the most energetic events in the universe. Gamma-ray bursts happen when massive stars collapse or when neutron stars collide, releasing more energy in a few seconds than the Sun will emit in its entire lifetime. These bursts are visible across billions of light years, which makes them useful as markers. By mapping where gamma-ray bursts occur, astronomers can infer the distribution of galaxies and matter on the largest scales. What they found was a structure roughly 10 billion light-years across. 10 billion light-years. That's not just beyond the limit. That's nearly 10 times larger than structures are supposed to be. The Hercules Corona Borealis Great Wall, if it's real, spans a significant fraction of the observable universe, which is about 93 billion light-years in diameter. This structure stretches across more than 10% of everything we can see. To put that in perspective, imagine standing on Earth and looking up at the Milky Way. Our galaxy is 100,000 light-years across. The Hercules Corona Borealis Great Wall is 100,000 times larger than that. If the Milky Way were the size of a coin, the Great Wall would span about a mile. If the Sun were a grain of sand, the Great Wall would stretch farther than the distance from the Earth to the Moon, thousands of times over. Comparing it to Andromeda doesn't help much either. Andromeda is 2.5 million light-years away, close enough that we're on a collision course. The Hercules Corona Borealis Great Wall is 4,000 times farther across. If you shrank Andromeda down to the size of a marble, the Great Wall would be the length of a football field. Even Laniakea, that immense heaven containing 100,000 galaxies, is only 500 million light-years across. The Hercules Corona Borealis Great Wall is 20 times larger. If Laniakea were a small room, the Great Wall would be a skyscraper. And the observable universe itself, that sphere of space from which light has had time to reach us since the Big Bang, is about 93 billion light-years across. The Hercules Corona Borealis Great Wall is roughly a tenth of that. It's not just a structure within the universe. It's a feature so large that it challenges our understanding of how the universe is structured at all. The problem is that structures this large shouldn't exist, not according to the cosmological principle, which is one of the foundational assumptions of modern cosmology. The cosmological principle states that the universe, when viewed on the largest scales, is homogeneous and isotropic. Homogeneous means it's the same everywhere. Isotropic means it looks the same in every direction. On small scales, obviously, the universe is lumpy. We have planets, stars, galaxies, clusters, superclusters. But zoom out far enough, and those lumps should average out. The universe should start to look smooth, like a pointillist painting where individual dots disappear when you step back. The Hercules Corona Borealis Great Wall doesn't fit that picture. A structure 10 billion light-years across is not a minor fluctuation. It's a dominant feature. If structures like this are common, then the cosmological principle might not hold on the scales we thought it did, which would mean our models of the universe's evolution need to be reconsidered. Some astronomers question whether the Hercules Corona Borealis Great Wall is even real in the way we think of structures. The identification relies on the distribution of gamma-ray bursts, and there's debate about whether those bursts truly trace a coherent structure or if they're just a statistical clustering that doesn't correspond to a physical wall of matter. Gamma-ray bursts are rare and hard to observe. The sample size is small. It's possible that what looks like a massive structure is actually just a chance alignment, a pattern that appears meaningful but isn't. On the other hand, other large structures have been confirmed through different methods. The Sloan Great Wall was mapped using galaxy surveys. The Boss Great Wall, another enormous filament, was identified through similar surveys and spans about 1 billion light-years. These structures are real, and they fit, just barely, within the models. The Hercules Corona Borealis Great Wall is different, mainly in scale. If smaller versions exist and are real, why couldn't a larger one be real too? The question matters because structures this size carry information about the early universe. The cosmic web we see today is an echo of the conditions shortly after the Big Bang, when the universe was just a hot, dense soup of particles. Tiny quantum fluctuations in that soup got stretched out as the universe expanded, and those fluctuations became the seeds of galaxies and clusters. By studying the largest structures, we're studying the amplitude of those initial fluctuations. If structures can be 10 billion light-years across, that tells us something about the initial conditions. It suggests that fluctuations at very large scales were stronger than we expected, or that our models of how gravity amplifies those fluctuations need adjustment. Dark matter plays a role here too. About 85% of the matter in the universe doesn't interact with light. We can't see it directly, but we know it's there because of its gravitational effects. Dark matter is what holds galaxies together and what forms the scaffolding of the cosmic web. Galaxies form along filaments of dark matter, like beads on a string. The distribution of dark matter determines where galaxies appear and how they cluster. If the Hercules Corona Borealis Great Wall exists, it implies an enormous concentration of dark matter stretched across 10 billion light-years, a filament so massive that it defies the usual limits of structure formation. And then there's dark energy, the mysterious force driving the universe's accelerated expansion. Dark energy works against gravity. While gravity tries to pull matter together into structures, dark energy pushes space apart, making the expansion of the universe faster over time. The balance between these forces determines how large structures can grow. In the early universe, gravity dominated, allowing structures to form. But as the universe aged and expanded, dark energy became more influential. Today, dark energy is the dominant force on cosmological scales, and it limits how much more structures can grow. The existence of the Hercules Corona Borealis Great Wall suggests that either dark energy wasn't as strong in the past as we think, or gravity was more effective at forming large structures than our models predict. There's also the possibility that we're misinterpreting what we see. The universe is expanding, and that expansion stretches space itself. Light traveling from distant galaxies gets stretched too, shifting toward the red end of the spectrum. This is called redshift, and it's how we measure distances on cosmological scales. The greater the redshift, the farther away an object is, and the further back in time we're seeing it. When we observe the Hercules Corona Borealis Great Wall, we're not seeing it as it is now. We're seeing gamma-ray bursts that happened billions of years ago, their light only now reaching us. The structure we're mapping is a snapshot of the universe's past, and the expansion of space means that distances have grown since then. It's hard to visualize, but imagine taking a photograph of a city and then watching that city grow for a decade. The photograph shows the city as it was, but the city has changed. The buildings are farther apart now. New roads connect them. The distances in the photograph don't match the current distances. The same thing happens with cosmic structures. The Hercules Corona Borealis Great Wall, as we observe it, is a historical structure. The galaxies within it have moved. The filament has evolved. What we're seeing is light from different parts of the structure that left at different times, all reaching us now. That makes it tricky to say with certainty that this structure is 10 billion light-years across. It's more accurate to say that the light we're observing suggests a structure that spanned 10 billion light-years when that light was emitted. Today, accounting for the expansion of space, the physical size would be even larger. But whether it still exists as a coherent structure, or whether it's been dispersed by expansion and the influence of dark energy, is unclear. What's clear is that the universe on the largest scales is more complex than we once thought. The idea that everything smooths out into uniformity at cosmic scales is neat and mathematically convenient, but reality doesn't always cooperate. The Hercules Corona Borealis Great Wall, whether it's a true structure or a statistical artifact, is a reminder that the universe can surprise us We've mapped galaxies, measured the cosmic microwave background, built models that explain the universe's evolution from the Big Bang to the present. And yet, we still find things that don't quite fit. Maybe the cosmological principle holds, and structures like this are rare outliers, statistical flukes that don't undermine the overall picture. Maybe our models need refinement, small adjustments to account for variations we didn't anticipate. Or maybe there's something deeper we're missing, some aspect of how gravity, dark matter, and dark energy interact on the largest scales that we haven't fully understood. The Hercules Corona Borealis Great Wall sits out there, or did, billions of years ago, a thread in the cosmic web so vast that it spans a noticeable fraction of the observable universe. If you could somehow step outside the universe and look back at it, seeing all of space at once, you'd see the web in its entirety. Filaments of galaxies crisscrossing the void, clusters glowing where the filaments intersect, voids dark and empty, and somewhere in that tapestry, a thread longer and thicker than almost any other, a wall of matter stretching across 10 billion light years. From our perspective, it's almost invisible. We can't see the structure itself. We infer it from gamma-ray bursts, tiny flashes of light scattered across the sky. Each burst marks a dying star, a collapsed core, an explosion that briefly outshines entire galaxies. By mapping those bursts, we trace the outline of something so large that it exists beyond intuition, beyond the scales we evolved to comprehend. Standing outside on a clear night, looking up at the stars, you're seeing light from distant suns. Some of those stars are hundreds or thousands of light years away. The light hitting your eye left those stars before you were born, in some cases before human civilization began. You're looking into the past, and when astronomers look deeper, using telescopes that can detect light from billions of light years away, they're looking much further back, seeing galaxies as they were in the early universe, when stars were first forming, when the cosmic web was just beginning to take shape. The Hercules Corona Borealis Great Wall is out there in that deep past, a structure so old and distant that its light has been traveling toward us for most of the universe's existence. By the time that light reaches us, it's faint and redshifted, stretched by the expansion of space. We capture it with instruments sensitive enough to detect gamma rays, the highest energy light there is, and we reconstruct a map, and on that map, we see hints of something enormous. It's strange to think that the largest structure in the universe might be something we're not even sure exists. We can't visit it. We can't observe it directly. All we have are patterns in data, correlations between distant events, and models that try to explain what those patterns mean. But that's how cosmology works. We're studying something so vast and so far away that direct observation is impossible. We're piecing together the universe from echoes and shadows, inferring the whole from fragments. And yet, despite the uncertainty, despite the vast distances and the limits of our knowledge, we've mapped the universe out to scales that dwarf everything familiar. We've traced the cosmic web, identified superclusters, measured the expansion rate, and pushed our understanding to the very edges of the observable universe. The Hercules Corona Borealis Great Wall, real or not, is a marker of how far we've come. A century ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Now, we're debating whether a structure 10 billion light years across fits within our models. There's something humbling about that, not in a way that diminishes us, but in a way that puts things in perspective. The Earth is small compared to the Sun. The Sun is small compared to the largest stars. Those stars are small compared to galaxies. Galaxies are small compared to superclusters. And even the largest superclusters are just threads in a web that spans nearly 100 billion light years. At each step, the scale expands, and what seemed vast becomes a tiny part of something larger. And we don't know if that's the end. The observable universe is just the part from which light has had time to reach us. Beyond that, space continues. We don't know how far. The universe might be infinite. It might curve back on itself. It might be one of many universes in a larger multiverse. We don't know. All we know is what we can see, and what we can see is already almost beyond comprehension. The Hercules Corona Borealis Great Wall is the largest known structure in that observable universe, a filament of galaxies stretching across 10 billion light-years, marked by the faint echoes of dying stars. It challenges our models, raises questions about the uniformity of the cosmos, and reminds us that even our best theories are still incomplete. Whether it's a real structure or a mirage, it represents the edge of what we understand, the boundary between the known and the unknown. Looking up at the night sky, the stars seem fixed and eternal, but they're not. They're moving, orbiting the center of the galaxy, drifting through space as the galaxy itself moves through the cosmic web. The Milky Way is falling toward Andromeda. The local group is falling toward the Virgo cluster. The Virgo cluster is part of Laniakea, which is being pulled toward the Great Attractor. Everything is in motion. Everything is connected, even across distances so vast that light takes billions of years to cross them. And somewhere, woven into that motion, is a thread 10 billion light-years long, a wall of galaxies so large that it might reshape how we think about the universe itself. Or it might be nothing, just a pattern in the noise, a trick of distance and time. Either way, it's there in the data, a reminder that the universe is stranger and larger than we can fully grasp, and that the more we learn, the more we realize how much we still don't know.